Hey everyone, in this video we're going to be talking about the inverse of a matrix. Okay, so previously we talked about matrix operations in the last video. Now we're going to focus on the inverse of a matrix. And so if we have an m by n matrix A, it's said to be invertible. If there's another matrix, we'll call it C, such that if you multiply left and right, so C times A and A times C, in both cases you get the identity matrix. And so basically what invertible means is that the matrix has an inverse. That's the easy way to remember it. So a matrix is invertible if it has an inverse. And an inverse exists if you multiply your matrix, you get back to the identity. So to make you understand this very simply, just think about what you know with, let's say, multiplication of numbers. So if I had, let's say, maybe the number 5, and I times it by 1/5, I would get to 1. Same thing as 1/5 times 5 would still give me 1. So think of the inverse undoing the original. Okay? And so each matrix, when it has an inverse, it's unique. So here's just a small proof of that. So if we say that the inverse C is uniquely determined by A, it's because if we said, okay, maybe there's another inverse of our matrix. If you take a look here, we realize that that other matrix, that's the inverse, is actually just the original one. And then what we denote the inverses as is A inverse. So you've seen this notation in the past, probably from algebra, and so that's going to be our inverse notation for our matrix A. And so in general, A inverse times the original equals the identity matrix, and you can change the order. A times A inverse, you'll also get the identity matrix. Okay, so we have a few theorems to go over. The first one is regarding a 2 by 2 matrix. So specifically, if we have a 2 by 2 matrix, then its inverse is defined as the following. Okay, so this one is sort of a thing where you memorize it. So let me just make sure you understand. Look what happened inside the matrix. You switch A and D, A and D swap. Okay, they swap locations. And then you put minus signs on B and C. All right, so that's what you do inside the matrix, but you also have to do this division out front, and you divide 1 over A times D minus B times C. This right here is called the determinant. And so AD minus BC is called the determinant of this matrix A. And so when we go larger, we're going to look at bigger matrices than 2 by 2s, and we're going to be able to compute the determinants and inverses of those. But for a 2 by 2, this formula is how you find the inverse. Okay? And so we can write that determinant as det of A. Just read it as determinant of A. And so if the determinant is 0, then this matrix is not invertible, meaning it doesn't have an inverse. But if the determinant is not 0, then it has an inverse. Okay, so if you're asked to find the inverse of a 2 by 2, you can check that it even exists by first just computing this determinant. If you get 0, then you can stop because it won't have an inverse. And so this theorem says that a 2 by 2 matrix is invertible if and only if the determinant is not 0. Okay, let's try out an example. We're going to find the inverse of this 2 by 2 matrix if it exists. So if we start with the determinant of A, notice it's not 0, therefore it does have an inverse, so we can keep going. And so just real quick, the formula, remember it was A times D minus B times C. That's how you get the determinant of a 2 by 2. All right, and then using our formula, we fill in the fact that the determinant was 1 right here in this denominator. And then we just swap what was A and D, so that's -7 and 2 swap places. And then we would just put minus signs on B and C. And then simplify. And so A inverse is just this matrix right here. And so anytime you're not sure if you did it right, you can always verify. So let's go ahead and check for this one. So we're going to multiply A times A inverse. And remember what we should get. Anytime you multiply a matrix times its inverse, you should get the identity matrix. And so let me just kind of remind you how this goes. We did matrix multiplication before, but I want to make sure you understand because you're going to be doing it more in this section. So it's row 1 from the first matrix times column 1 for the second matrix, and that's going to go in the first entry here. And then row 1 times column 2 is going to go in the second entry here, and then so on. And so notice, remember these subscripts? I'm calling the second matrix B, just to clarify. And so this is saying the entry from row 1, column 1 times the entry from row 1, column 1 of the second matrix, plus entry row 1, column 2, which is 5, times entry from row 2, column 1, which is 3. Okay, so it's just 2 times -7 plus 5 times 3 for our first entry. And so we do that for all 4 spaces in our answer. And notice what we get when we simplify. We do get the identity matrix. And so technically you would want to verify the other direction as well. You should get I both times. And that lets us know that we did in fact find the correct inverse here of our matrix A. Here's another theorem. If A is an invertible n by n matrix, meaning it has an inverse, then what's true is for each vector B in Rn, the matrix equation or vector equation Ax equals B has a unique solution x equals A inverse times B. So just take a look at this real quick. If you were to substitute A inverse B right here for x, look what would happen. It would be A times A inverse, which would think of it as undoing each other, giving you the identity, which is just the identity times B, which is B. And so let's just go through the proof of this real quick. So we'll say B can be any vector in Rn, and then let's do exactly what I was just mentioning. Substitute x for A inverse B, and then if you group these together, so just change your association here, A times A inverse is, just think of it as like 1, but it's the identity matrix, and that just gives you B. And so that is a solution. And what we also have to prove is that it's a unique solution. And so to show that it's a unique solution, we're going to say U is any solution, okay? And that we're showing that it must be exactly what we got up here, A inverse B. Okay, so we have A inverse times A times U equals A inverse times B. And so right here, A inverse times A, that's just the identity matrix. So we have I times U equals A inverse B. Therefore, I times U is just U, so U must equal A inverse B. So just a quick proof of this theorem. Okay, so let's take a look at an example using that theorem. So we're going to solve this linear system. Notice what we're solving for. It's going to be our vector x. And so the first thing we want to do is write the matrix A, which is just the coefficient matrix from this system. So notice from equation 1, coefficients are 3 and 4. Equation 2, the coefficients are 5 and 6. And then what this is our going to be a matrix equation, and so it equals the vector B, which is 3, 7. All right, so according to our theorem, we need to find the inverse. And so using what we just did for our inverse of a 2 by 2, we can compute that the inverse of this matrix is 1 over the determinant, which happens to be 1 over -2, times, notice we switched A and D, put minus signs on B and C, and then we have that A inverse is this matrix right here. Okay, so now that we found that, according to our theorem, since the inverse exists, we know that the solution to this equation is x equals A inverse times B. So now all we have to do is multiply what we just found, A inverse, times our vector B right here, which is 3, 7. And then we get that x, after we do this multiplication, is just 5, -3. And you can always check if you want to make sure you got this right. You can either multiply A times x, and then you're going to get B. Or if you want, you could just plug in 5 for x1 and -3 for x2, and you'll get the same thing here, 3 and 7. And so just a quick note, using this theorem is what we just did to find x, but to reduce this matrix, a row reduction is usually faster for solving this augmented matrix when we're working with matrices larger than a 2 by 2. So this one was a 2 by 2, so this didn't take too long. And another theorem for us here, this one has 3 parts. And so we're just learning about our inverses of our matrix and what we could say about a matrix that has an inverse. Okay, so if your matrix is invertible, then its inverse is also invertible, meaning that you can find the inverse of the inverse matrix. Just think of it as undoing itself. So this is saying A inverse. If you take the inverse of that, hopefully this makes sense, you get back to the original. Think of these as undoing each other. Part B, if A and B are n by n invertible matrices, then so is their product. So this is kind of a nice theorem, part of the theorem. And so the inverse of AB is the product of the inverses of A and of B in reverse order. So that's right here in notation. So the product AB, you multiply them, you want to take the inverse. It's equivalent to if you take the individual inverses of A and B, but when you do the multiplication, you have to reverse the order. And remember, with matrices, the order matters when you multiply, because most of the time, when you multiply two matrices, it doesn't stay the same if you change the order. And so we learned about something very similar to this when we were learning about the transpose of a matrix. And so that kind of brings us to part C here. If A is an invertible matrix, again, that just means it has an inverse, then so is its transpose. Remember, transpose of a matrix just means you switch the rows and columns. And the inverse of A transpose is the transpose of A inverse. So in symbols, it looks like this. A transpose, you want the inverse of it. It's exactly the same as if you know the inverse of A, and then you transpose that. So sometimes you can maybe start with the left side of this equation, or you could start with the right side. It just depends on what's easier for your matrix that you're working with. Okay, let's talk about elementary matrices now, and then we'll look at an example for how to find the inverse of a bigger matrix. We'll do a 3 by 3. So an elementary matrix is one that's obtained by performing a single elementary row operation on an identity matrix. So here's an example. So this matrix E is found just by doing one operation, -4 times row 1 plus row 3 on this 3 by 3 identity matrix. So just defining what we call an elementary matrix. And so each elementary matrix is invertible, meaning it has an inverse. And an n by n matrix E is invertible if and only if E is row equivalent to an identity matrix. So like this one here. Then the inverse of E is an elementary matrix of the same type that transforms E back into I. All right, so what we're getting into is how to find an inverse of a matrix for anything larger than a 2 by 2. If we have a 2 by 2, we can use the formula we did earlier, but a 3 by 3, 4 by 4, and so on, we're going to use this process. So first, here's our theorem for. An n by n matrix A is invertible if and only if it's equivalent to an identity matrix, and in this case, any sequence of elementary row operations that reduces A to this identity matrix. That would also transform an identity matrix into a inverse. Okay, so what this theorem is talking about is basically this algorithm down here. How we're going to be finding these inverses of our matrix is we're going to set up a matrix where we have our matrix A on the left, and then our identity matrix of the same size on the right, and that forms one matrix. And what we do is we actually end up row reducing A until it becomes I. We'll do an example so you see it. But A is going to become I, an identity, and then what the result is when we do this process is that the right side of our matrix is now the inverse. So it's a pretty nice process once we get to the answer. Okay, so here's how this works. Let's say we have this 3 by 3. We're going to try to find the inverse if it exists. So once again, if this was a 2 by 2, we could just use our formula from earlier. But for a 3 by 3 and bigger, we're going to use this process. So what you do is you set up this matrix where the left side is, the left columns is A, and the right columns is the I, but the same size as A. So in our case, notice we have the 3 columns and rows from A right here. And then we have the 3 columns and rows from the identity matrix right here. So if it helps, you can put a little dashed line down the middle. This might help some of you stay organized or see what's going on. And what your goal is, just so you know where we're heading, we are trying to get I on the left. So you don't have to focus on the right as far as what you're trying to obtain, because as you focus on the left side, the left 3 columns here, so we get 1s in the diagonal and then 0s everywhere else, which is our identity matrix. So 1s here and then 0s here, 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 and here. By doing our row operations, then what happens is by our work, just by doing our work on the left side, what's in the right side then becomes a inverse. Okay, so the very first thing you have to do is set this up. You have to put A in your left columns and I in your right columns, and then you just start reducing. Okay, so let's just take a look at the first step here. We can get this equivalent matrix. This one's done really quickly just by swapping. So we can just say row 2 swaps with row 1, and then we're on our way. We have a 1 in our top left corner, we have a 0 underneath it. That actually gives us a 1 in the diagonal here as well. So this is good. We're trying to make this an identity matrix on the left. Okay, so here's the result. Okay, so you would just go through your process, and again, if it helps, put a dashed line in the halfway mark on all of these, and you do your row operations. That, remember, we've talked about this before. You can add rows, you can multiply rows by non-zero constants and then add them, and you can swap rows. Okay, so you're trying to get 1s in the diagonal and 0s everywhere else, and then once you get there, which is on this last version down here, notice what you have the identity matrix in your left columns, your 3 columns on the left, and what that gives you as a result is that the right 3 columns right here actually represents your inverse. So again, just to hopefully clarify, you focus on making the identity matrix on the left, and as you're working, just as a result of your work, then your right 3 columns, in this case because it's a 3 by 3, by default it becomes the inverse. And so our theorem shows that since A was equivalent to an identity matrix, as we focused our attention on the left columns, that A is invertible, and its inverse was the right columns. And so that is A inverse. So this process is how you can find your inverse matrices of a matrix size 3 by 3 or larger. You can do this for a 2 by 2 if you want. It will work. But normally the formula that we looked at earlier was faster. So in general, if you are asked, hey, what's the inverse of A? You're going to put a matrix together where A is the left columns, and then you would put the same size matrix but I in the right columns, and then you do your row operations. So I'll just say like dot, 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 pardon my dots, and then after some steps, some row operations, you end up with I on the left side. And then from your work, what ends up being on the right side is your answer to the question, which was, what was the inverse? Okay, and so you can always check. So if you're not sure if you got it right, you can multiply A times A inverse, or the opposite, A inverse times A, and then you should always get back to the identity anytime you multiply a matrix times its inverse. So if you think you didn't do it right, or you might have missed a step somewhere, or you just wanted to verify, this is the way to do it. Just multiply and make sure you get back to the identity. All right, the last thing to mention is just some facts for us here. So it's really not actually necessary to check both directions. We had looked at A times A inverse. You can check A inverse times A to make sure that equals I as well. But if you just do one out of the two and get that the result is I, then you're good to go. So in this case for I, just for notation purposes, we usually denote the columns with E's. So E1, E2, and so on. Then the row reduction, when you have your matrix set up where A is your left columns and I is your right columns, when you reduce it to I on your left columns, and then the result is A inverse on the right columns. Exactly what we just did. We can actually view this as the solutions to n systems of equations. Okay, so where A times x equals column 1, E1, AX equals column 2, and so on, where the augmenting columns of these systems have all been placed next to A to form this matrix here. Okay, so this is equivalent to this one here. So A on the left columns, E1, E2, and so on the right columns, but those just represent I. And then the equation, A times A inverse equals I, along with the definition of a matrix multiplication, show that the columns of A inverse are precisely the solutions to this system of equations up here. All right, so just some facts for us. Okay, so that is how you find the inverse of a matrix. And remember, when a matrix is invertible, that's just a way of saying it has an inverse. So my advice is just to take your time, especially if your matrix is size 3 by 3 or bigger, because it's really easy to mess up on one step, and then you're off at the end with your answer. So just take your time and stay organized when you're doing this reduction from AI to A inverse. And then you'll get your inverse after you just do some steps. All right, that's it. Take care.